we motivated the introduction of neural networks using linear regression, logistic regression. Today we will be defining neural networks, shallow neural networks. The first topic is what is a neural network, the shallow neural networks. Okay. And then we will see that how we are using neural networks to create good nonlinear relationships. And then a brief discussion on why are neural networks good. Then we will move ahead to discuss about, we have discussed what are, we will discuss what are shallow neural networks, and then we will move ahead to discuss deep neural networks. And if we have time, we will go on to discuss optimizing deep neural networks, and that will continue over to the next week. So let's first revise. We will start by revising. So the first part is we have an input x, and we are defining a function. We define a function, we get the y hat, and we want that predicted y hat to be as close as y using a loss function between y hat and y. And we want to minimize the loss to get the very good theta, which defines the function. So geometrically, you can see there's x is again known. Then if there's f is kind of fixed, theta is unknown, we need to find theta. And then we have y hat, and again y hat is unknown, but let's not mark that. We will then go ahead to loss, which is again fixed by us, and then we have the known y, and we want to find the best. We want to minimize this to get the best theta. Okay, simple. And then we also did the circuit diagram. So we have x1, x2, xn, and we have the weights which we are learning. This weights, sorry. So we have x1, x2, xn, this inputs, and we have the weights w and b, and we are trying to find this parameters w. These are parameters theta. We add them here. We do the summation, and then we get the final y hat. Okay, this is for linear regression. Understand, this is for linear regression. This is for linear regression. Let me just make it small. This is for linear regression. So we get y hat, and there is loss function, which can be MSE or MAE, and like max mean square error or mean absolute error, which is also computed by the y. In logistic regression, we did the same thing. Everything is fine. We had the input, we have the weights, the parameters theta, we add them. Okay, then we have a softmax layer, which gives, if you remember from last video, if you've not watched the video, please go and watch it. It's on YouTube. I already shared it. The y1, y2, y3 hat, and we have corresponding y1, y2, y3 from y. So these y1s are the class probabilities, and we find the loss function, which is usually cross entropy loss. We will not go into details at how there's a mathematical theory, a probabilistic theory, which talks about using something called maximum likelihood estimation of how we have reached those specific loss functions. We will not talk about that. We will just assume we have discussed that the loss functions are good enough to do our work, and we will assume that, and then we will do our work. But if you want to read more about it, if you go to the my YouTube video that I've shared with you, and in the description I have given a reference book, so please read that book. The 4 or 5, 6 chapters I have referred. So those are very important if you want to dive into it. Okay, so all good till this point of time, guys? Can you give a thumbs up? So the next question is, okay, so observe that these are all linear relationship. If you observe here, these are all linear relationship. There's summation and weights, all these are linear relationship. even logistic regression also, it's the main core part is linear relationship. Of course, the softmax is transforming those things, those outputs to probability. So that's why the nonlinear relationship even comes up there, because we want to change it to positive, non-negative, and then divide by the sum to get it less than one, right? But these are mostly the main parameters. The relationship with the parameters are linear. So the question therefore turns out that what can we do to learn nonlinear relationship? Because we know that most of the functions out there are nonlinear. Okay. So how to learn nonlinear relationship? And we will see that neural networks tries to solve that problem. So to understand this in a much more detailed way, and we first should define what is a neural network. What is a neural network? So we define it like this. So the good thing is that neural networks have special cases of linear and logistic. But let me show you what neural networks are actually. To make it easier for explanation purposes, we will use certain notations and we will explain it first. First of all this relationship that we are doing here, these are all linear relationship, right? So we will try to understand what's happening. So let's see that, let's assume this h1 is, so what is happening, the input are x1 x2 x3, three numbers. Okay, so what we are doing here, we have w1 for h1. Okay, let's like do like w1 for h1. We have for wh2, for x1 to h2 the weights, let's call it w12. For x2 to h1, let's call it w21. 2 for x and 1 for h. For 2 to 2, we let's call it w22. For 3 to 1, let's call it w31. For 3 to 2, let's call it w32. Interestingly, these numbers can be arranged in a beautiful format, and maybe you could have guessed from now. So what's happening is that we can actually write it as a matrix form. So if this is x1 x2 x3, the question is that what is this w such that it turns out to be h1 comma h2. This is the question. So for x1 we have h1, so first one is w11. Let's make it a bit bigger. Okay. So understand this. For h1, to get h1, we have w11. For x2, we have w21. For x3, we have, sorry, I'm doing something wrong. For h1, observe, yeah, I think I am doing something right. w31. Okay. Let's make a change. The change in the nomenclature, let's make it different. So what we will do is that we will, because in a matrix, what we do is that we do w1, 1 is for this. Okay. 1 is for the column and j is for the, just give me a minute. Just give me a minute, okay? Okay, so for the nomenclature, so essentially the column is for the 1 and this is 2. So what we'll do is that we will use the following nomenclature. If it is going to h1, we will name it like 1 if it's going to h1. Okay, if it's going to h1, we will make it 1. We will start with 1. Okay, similarly here it will be w2 1 because it's going to h2. So w2 2 is for h2 and 1 is for this. And similarly, sorry. And this one is w3 3. Okay. Yeah. Yeah, this one will be w2 2. Sorry, this one will be 2 3. So if you observe now that h1 is now coming from w11, w12, and w13. 1, this, and this. And w21, w22, and w23 is h2. So this is, yeah, all of you understood this, guys? V1. So observe that this is a, and plus there is a, remember that this is a linear operation, but also sometimes there is bias added to each layer. So the same bias is added here, let's say. Okay. So what we can do is that we can say that this, so BB is it, so plus BB is this, right? So what we will say that this is W, we will call this as X and we will call this as just B. And this is H. So simplifying, we can write like this where H is equal to Wx plus B, where these are learnable. These are parameters. Theta is equal to W and B. These are parameters to be learned. So what happened is that instead of this complicated diagram, we using linear algebra, using matrices, we made it very simple looking. Okay, we made it very simple. Simple. It looks simple. That H is equal to this. But still now, it's linear. Everything is linear here. Everything is linear here. Okay. All good? Can you give a thumbs up, guys? So this is very important to understand, guys. So what is neural networks? So remember, this can be multidimensional. So what is neural networks? So we have done everything linear here. So neural network is nothing but is an extra added step. So we have these parameters, this, we have H, we have another layer. So this is what all currently are linear. But there is another non-linear layer by something called an activation function. Which you can call this as output and this as H final. Okay. So H is equal to the hidden, it's called the hidden layer, the hidden output, you can say, is nothing but the activation function of Wx plus B. Remember this. This is very important. It's called hidden. Okay. Now you may think that it's just a single number, but it can also be multidimensional. Like this. In this case, it's 2. So it's a two-dimensional. So you can observe. So one observation. So I will come to what are this. I will come to this fact. One important question is that what are these nonlinear functions? What are these activation functions? I will come to this absolutely. But before that, let's understand that this multidimensional nature. So understand this multidimensional nature. It's very simple. If you remember that this is W, okay? This W is a matrix of n cross n. So M is this and n is this. And this, it's multiplying with x, which is nothing but m cross 1, n cross 1. So n is what? N is the number of inputs. Input numbers. And the output plus there is a B. This B is again but m cross 1, because when you multiply two matrices m cross n times n cross 1 turns out to be m cross 1. So this is also m cross 1. So sum will be again m cross 1 h. So it's nothing but there are n inputs, and after this there is m outputs. M outputs. So we are actually compressing this information into this format. Wx plus b is equal to h. That's why this equation is very important. It's a matrix. Okay. So we can write this W. So this W is very important. This is so pretty and so simple to write. And it encodes so much of information. Okay. So this M and N, the dimensions of W talks about the input and output number of neurons. Got it, guys? So in this case, we are talking about neural networks. We first discussed, to revise, we first discussed what linear operators can be expressed in matrices. Second, we simplified the circuit diagram to matrices, in terms of matrices. So it made it very simple. And now we are going to discuss neural networks as sequence of this linear and nonlinear layers. Sequence of linear and nonlinear. I have not discussed what are nonlinear, but this is the main function that turns out to be. A is nonlinear. A is an activation nonlinear function. Before we discuss what are activation functions, I discuss the multidimensional input and output nature of this entire equation. Got it? So now let's understand nonlinear activation function. What are this? So all of you good till this point of time, guys? All good? Jordan, Ivan. So now let's understand the nonlinear activation functions. What are these nonlinear activation functions? So these nonlinear activation functions are what? There are multiple examples. One is, so what are the properties of this? Essentially, it induces non-linearity into the function. Now, why, I will come to that later. Why? I will come to that later in details with a lot of examples. But the main idea is it can learn varied amount of information relationship. And we'll come to that again. Universal approximation theorem. I will come to this. I will come back to this. But let's see some examples first. What are used? I will discuss 4 of them. One is step function. One is ReLU. One is sigmoid. One is tanh. So step function is nothing but function is nothing but this function. So it's a simple function. It converts everything to 0 and 1. So let me just confirm once step function is step activation. Just give me a minute. I will just confirm whether it's 0, 1 or minus 1, 1. So there are 2 type of functions. So it can be 0, 1 or minus 1, 1. Okay. So what it is, it looks like this. This is x. This is the activation function a of x, the activation function a. So if it's greater than 0, if it is less than 0, then 0. If it is greater than equal to 0, if it's less than equal to 0, then 0. If it is greater than 0, then it's 1. So f a of x is 1 if x is greater than 0, 0 if x is less than equal to 0. Okay. Sometimes it can be also 1 if x is greater than 0 and minus 1 if x is less than equal to 0. Less than 0 and 0 otherwise. It can also be like this. Okay. So it can also be like this. Just for clarity. So yeah. So this is step function. This is a basic you can see it's non-linear like this. It's non-linear like this. All of you got it, guys? The whole idea is to build, if you remember my properties of good functions. Jatin, did you get it? If you remember my properties of good function, one is it should be simple. And yeah, it should be simple. And yeah, I will talk about what nonlinear things it actually, I will show you an example, so do not worry about that. ReLU is another one which is brings some nonlinearity. One is ax is equal to max of 0 comma x. So what does it mean? It can also be written as x if x is greater than or equal to 0 and 0 otherwise. The diagram of it looks like this. X, x. If x is less than 0, then 0. Then if x greater than 0, then x. Simple. So for tanh, so let's see the tanh. I forgot the exact activation function formula. So yeah, the tanh is again. So before discussing tanh, let's discuss sigmoid. The sigmoid is this a of x. Sorry. is equal to 1 plus 1 minus, like, or you can say, like, if you remember yesterday, the probability essentially transforms everything between 0 and 1, like this. Okay, now you can say, oh, it's for probability. Yes, it's for probability, but again, it's used because often what happens is that, let's say for raw data, these outputs are very large. So they essentially, the whole idea of nonlinear is to induce nonlinearity, but also keep it kind of, uh, initially it was thought it keep it bounded. Okay, that's why sigma and all these things came up, but then there was issues, so ReLU came out. So it keeps non-linear very simple, piecewise linear, but also it's unbounded. So there you can see that sigmoid, tan h are bounded, step function is also bounded, you will see that. So for example, this, if you draw it, it will turn out to be something like this. It transforms everything between 0 and 1. So what happens is that it turns out something like this. It's between 0 and 1. Okay, so it's between 0 and 1. Perfect. All of you got this sigmoid thing, guys? Again, these are basic nonlinear functions. So now tan h is a of x is equal to e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. Essentially, it's just extension of the sigmoid, but now it should be between 1 and minus 1. So it looks like this now. So it's 1 and it's minus 1. Okay. So these are basic examples. But the idea is this, that there are many other examples like leaky ReLU, etc., many other different examples. But the core idea is to remember that this induces nonlinearity. Okay, this induces nonlinearity, and we will understand why nonlinearity is important. So to make you understand why nonlinearity is important, let's solve this problem called XOR problem. So what this problem is saying? Let's understand this. So the problem is this, that you have 4 data points: 1, minus 1, minus 1, minus 1, 1, minus 1, and minus 1 and 1. Okay, and you see that the 1 and 1, 1 and minus 1, minus 1 is opposite, like are colored green, which let's define it minus 1, and red and red are defined as different colors, different classes. Let's call it 1 and 1. The class numbers, the class levels. So the question is this, that can we, so first of all understand we cannot solve this using a linear, just linearity, because you see the boundary here, it's non-linear. The boundary here is non-linear. So it's not a linearly solvable problem. Cannot solve it linearly. Okay. So what we will show now using a linear neural network. So, okay, before I define this, I need to actually discuss with you that what this is doing, this neural networks are doing. So let me define that first. So a shallow neural network is defined as a shallow neural network is defined as this y hat is equal to f of x comma theta, where f is nothing but an activation function and a linear layer. Simple. So what is happening in this activation function? So let me show an example. Let's say x is equal to minus 1, 1. W is equal to, let's say, 1, minus 1, 1, 0. And B is equal to minus 1, 1. An activation function, let's say ReLU. That is max of 0 comma x, whichever is the maximum among 0 and x. So let's see what it will turn out to be. So y hat, this is a shallow neural network. So this output, so we can rewrite this as this WB. Okay, let's call this output, and then activation. This is H. So this output is called a hidden layer. So this is written together. And this is it's actually together. This is called a layer. This is hidden. So y hat is defined as what? ReLU of, so let's define ReLU of wx plus b. So let's get wx plus b. So wx plus b is this 1 minus 1 1 0 minus 1 1 plus minus 1 1. So we get ReLU of, let's calculate this, minus 1 1 1 minus 1 is minus 2, minus 2 and minus 1, minus 2 and minus 1, we get 3 comma 0. Okay, so ReLU of 3 comma 0. Now we are applying ReLU on, ReLU is defined on a single number, so we are applying ReLU on each of the elements of 3 and 0. So we get ReLU of 3 comma ReLU of 0, which turns out to be 3 and 0, because those are the max, like among max of 0 comma 3 is 3, max of 0 comma 0 is 0. So this is the output. So understand that it's a linear. Linear is happening over the entire x, but ReLU is acting pointwise on each one of them. Pointwise, non-linear. This language actually helps you remember this. And the output of it is a hidden layer. Okay, in this case, it's a function. So this is very important. Did you understand the definition of a shallow neural network? Yes. So theta is equal to W comma P parameters. Now let's try to solve this XOR problem. Again, I was talking about this problem that there's 4 points. You can see the boundary is non-linear, so cannot solve it linearly, right? So the question is that if we cannot solve it linearly, then how do we solve it? Of course, non-linearly. And we will show that using this simple shallow neural network, we can solve this. So what we do? So we have to define the weights now. And we'll see what we can do to define the weights. So we have to define these weights. X. Understand the x can be any 4 of them. X is x1, x2. We do not know W, so we have these 4 numbers. To remind you, let's call it W11 for H1. Since it's going to H1, this is W12. This is W21. This is W22. So you have W11, W12, W21, W22, and there's an activation function. Let's call it ReLU. So we will use a different activation function here. Let's use another step activation function. So activation function of X is defined as 1 if X is greater than 0, minus 1 if X is less than or equal to 0. That's it. Simple. So the question is that can we find, and let's also call bias. We have a bias. Okay. Another important thing is that there is another, so after this layer, there is another set of weights. Here, let's call it W bar 1, W bar 2. Understand this. There's another 2 of layers. So what's happening is that the H is A of Wx plus B, okay, plus. So B I didn't write. I also don't know B. Plus, so this is H, sorry. And then there's another layer, understand this. And then there's another W hat, let's say. So then there's W hat of this entire thing. Plus another B hat, let's say, the bias. This is finally equal to Y hat. Okay. So there's another Y and there is also a bias here, B hat. There's also a bias here, B, in each one of them. The goal is to find these numbers. This one, this one, this one, and also this W hat. Understand this W hat is W hat 1, W hat 2, as shown here. And this is here. Yeah. So let's okay. So we have to find these numbers such that it works. So what do we want? We want to find those W hat, W, B, and B hat such that it turns out to be this as close as possible. And can we get exactly these numbers? And it turns out it does. So let's take an example. So let's take H1. So as I said, let's call this H1. So this element, the first element output is H1. So let's do this. So what we will do is that we will define H1 as this. So let's see. I'm wrapping it off so that so let's define H1 as this. The activation of x1 plus x2 plus x1 plus x2 plus. So the weights here are 1 into x1 plus 1 into x2 plus bias is 1. And if x1 plus x2 plus 1, let's see first. So output is 2, minus 2, 0 and 0, plus 1. So the 3, minus 1, 1 and 1. And there's the activation function, which is if greater than 0, then 1. If less than 0, then minus 1. So what do we do here is this. If greater than 0, then 1. So it becomes 1. If less than 0, it minus 1. It already minus 1, but let's rewrite it. This is greater than 0, 1. This is greater than 0, 1. Perfect. This is the H1. For H2, what we will do is activation of minus x minus 2 plus 1. Let's do that. Minus x minus 2 is minus 2 plus 1 is minus 1. And activation of that should be minus 1. Minus 1, minus 1. So 2. So because minus x and 1 minus x2. So 2 plus 1, 3. So it becomes 1. Because then if greater than 0, then 1. 1. So minus. So you can see this is again 0 because x1 plus x2. This is minus of x1 plus x2. plus 1. So x1 plus x2 is 1, 0 here. So it's 1 here, naturally, same as before. So this is the second neuron. So so you can see here the bias is kind of 1. So here you can see that W12 is equal to 1, W11 is also 1, and B is equal to 1. Here you can see that W21 is equal to -1, W22 is equal to -1, and B also is equal to, B is the same anyway. Now let's calculate this W hat 1 and W hat 2. And you can see so let's see. So W hat, so we will do H1 plus H2 minus 1. So H1 plus H2 minus 1 is 0, minus 1 is -1. H1 plus H2 minus 1 is 1, -1. 1 plus 1 minus 1 is 1. 1 plus 1 minus 1 is 1. So you can see we have got exact, this is y hat. We have got y hat exactly to be this. See. So zero loss. So what it tells you is that, so first of all, let's write here W hat 1 is equal to 1, W hat 2 is equal to 1, and B is equal to -1. So let's write this as a matrix. So yeah. So you can see that this is the entire thing. So let's write this as a matrix. So we have W as 1, 1. Oops. Just give me a minute, sorry. Okay, so we have W1 is 1, 1 is 1, W12 is 1, then -1, -1. B is 1, comma 1, right? And W hat is 1, comma 1. Okay. And here B is equal to -1. It's a single number though. That's why. Because the output is a single output. So this is the neuron. This is a shallow neural network for you which solve this problem. Now understand this, that this is not exact, but if you see that if there is a simple solution, a simple solution to this is nothing but, if you observe that it is nothing but minus of x1 comma x2, x1 times x2. If you see this, it's 1 times 1. If you do minus of that, it's exactly this value. So y is equal to nothing but this, right? Minus of x1 times x2. But the goal of neural networks is find great approximate solutions to complex relationships using simple operations like linear plus pointwise nonlinear. Do you see the point, guys? So observe that in this case, we are actually approximating minus of x1 times x2, that is with this relationship with this relationship that you have seen here, this one. We're approximating that. But this is the actual y minus of x1 comma x2. So understand this very carefully. This is very important. We're actually approximating this. This is the actual one. This is the approximate one. But the good thing is that we are getting close towards a solution. Did you understand, guys, Jaren and Vivan? So this is the actual relationship. This is very important. Now let's see some examples where. So this is taken from the book I have mentioned in the YouTube video. It's some examples of how we are building nonlinearity. Piecewise. So observe that. So take these examples. X1, X, and X is going to 3 hidden neurons. These are this. What you see? These are 3 lines, 3 linear relationships. Okay. Output 1, output 2, output 3. And there is nonlinearity AAA, which you get H1, H2, H3. And then you add them simply to get the final y hat. Okay. So this one is O1, this is O2, this is O3. Okay, 3 linear relationships. You get now ReLU of on ReLU activation. So this is A of O1, A of O2. So okay, so let me call it H1. This is the H1, this is the H2, this is the H3. Okay. Remember there is here W1. There are weights out here. So this is so now understand the ReLU is makes everything negative to be 0, right? That's why these are like this. Did you understand this, guys? How the activation map is happening here? This is the output, linear output, and the ReLU is happening here. Now there is, after this 3 hidden networks, there is another linear layer, okay, to get the final output. So let's say you multiply something like this to get, so it's like this is multiplied, let's say, by -2. That's why it's become 1 like this, by the multiplication of phi 1. In this case, I have taken it from the book, there the notations are different. In this case, it's probably multiplied by 1.5, and in this case it's probably multiplied by 0.9. So the height is a bit less. You see the height is here this, but here it's this. Here it's this, but it's actually increased here, it decreased here, and it has negative here. Now if we add them now finally to get y hat, so this is W1 hat L, W2 hat H2, W3 hat H3. So you can see that this is W1 hat, W2 hat, W3 hat. And this, when you add them, this is y hat is equal to sum of them. You can see that this becomes this nonlinear function, right? Did you get it, guys? This is when you add them. Now comes the fun part, that what happens This is why it works. First of all, we have built neural networks out of the simple elements. Now comes the universal approximation theorem, which tells you that why neural networks are good. We already have seen neural networks are built up of, it should approximate, and it's simple. We have already seen this is simple. Now is the time for approximate. So observe, in the similar to this, if you have just here you have output of 3 neurons, but if there are 5 neurons, it will be something like this. But the actual function is this dotted line. If there are 10 neurons, the output will be something like this. It's becoming slowly closer and closer. If there are 20 linear, so what it's saying is that, so read this line. With arbitrary, the universal approximate theorem proves that with enough hidden units, there exists a shallow neural network that can describe any continuous function with arbitrary precision. So as you increase the number of these units, so the error becomes less and less, and it's proportional. The error is inversely proportional to the number of hidden units. So you can arbitrarily approximate any good function. With neural networks. All of you got it, guys? Great. So this is why neural networks are good. So till now we have understood what are shallow neural networks, what is the relationship of neural networks and the nonlinear relationship between them, why are neural networks good. Now the time has come to talk about, so we have talked about deep neural networks, shallow neural networks. Now we will talk about deep neural networks. So one important thing is that, so observe that what we are doing, we're increasing the number of neurons here, like this. So what this will make is that this will make the matrix really huge, right? This will make the matrix really huge. So that is hard to store, right? So the question is that, so this is the width. This is called the width. Okay, this is called the width. Now, what the next part is that instead of growing it in the width, they ask that can we grow it into depth with smaller matrices. We have more number of matrices. So in this case, it was just a single matrix, right, with which you can approximate. Smaller, but more matrices. And it turns out, yes, you can. So universal, if you search universal approximation theorem, you will see that in depth also, in arbitrary depth, you can actually have very good approximation. Okay, you can have very good approximation. This is important. Did you understand, guys?
Wait, so can you just repeat?
So what I'm saying is that when it says that with arbitrary, so when we say that, with arbitrary linear regions or hidden units, so the number of, when I'm saying x to hidden number of hidden units, that means for a more complex function we need a more huge matrix. You see the number of the width number of hidden units. So width, so the width is number of hidden units, like x to how many neurons it's going to, h1 h2 hk, h capital N. It shows that as you increase n, the error decreases. But for complicated functions, we need really huge capital N, which is untractable by computer. We again need simplicity. So the question was, so this is called the width. The question was, now, can there be depth? Like x, let's say only 15 neurons, and then another 15 neurons, dash. Then another 15 neurons. So can you also do like this? So this way, see, the computer has no issue in computing sequentially, but it has a lot of issues in computing so many together at the same time. So smaller chunks, but large number of chunks, it's great because it's like a sequence. Because once you do the linear, once you do the, here you can forget the previous one and just focus on the next one. But here you cannot forget the previous one. You have to do it all together. So that's why it's issue. So it's like, instead of writing n as 2 into 100, you can also write n as 2 into 10 plus 10 plus 10 plus 10 plus 10, 10 times. This is easier for a computer. Do it sequentially instead of all together at the same time sometimes. Yeah, I mean, in the sense it's easier, means memory wise. So you cannot store so many numbers. Like I am saying, it's actually 10 to the power, let's say 10. It's not easy for computer to store so many numbers just for one single function. Do you see the point what I'm saying? So now why it's useful? Because here it's sequential. You first compute x to h1, the first layer, and then you can forget x, right? You don't need x. You don't need even the y and b. Now you can just save h1 and get the next w1 and the b1 to get h2. Make sense, guys, what I'm saying? So memory wise it's cheap. b1, did you get it?
Yes, sir.
Memory wise it's easy and cheap. So we cannot store a large huge matrix. Just give me a minute, guys. Okay. So yeah, and the interesting thing is that due to this memory storage, our brain also works in this. This is called hierarchical. So this first calculate h1, then use h1 for the next h2. This is called hierarchical. And this is also our brain. Our brain actually stores like this. Brain processes information like this. This is very important to understand. Our brain processes information like this. So that's why, in fact, that's why you can actually show that for a deep neural network, there's a result, you need exponential number of neurons, hidden units, to represent the same function which just takes k square in depth. So a lot of memory storage is because our brain actually stores information like that. So the whole idea is that we have better representation, better. So we will learn what it is. So this H1s, these representations are really useful because they are further used for the next step. These interesting representations are further used for the next step. And this is the reason is that this is how all the information is stored. This is a very important concept, guys. Okay. So very, very important. Because both depth and versus width is important. So probably I should write it here. So what are deep neural networks? Did you understand this, guys? Fully? So now deep neural networks. What are deep neural networks? As you can see, it's a hierarchical representation. So let me rewrite it first. Just a shallow neural network was this, right? W, B, and H. And then there's W hat and Y hat. So let's call this as W naught, B naught, and let's call this as W1 and B1. So we have, so this is shallow. So we have H is equal to W naught X plus B naught, and Y hat is equal to W1H plus B1. Now we wanted more hierarchical representations. So you see, this H is called a representation. Understand how human beings think. Understand this very carefully. We learned language over evolution, right? Birds cannot speak, but birds can have thoughts. So what happens is that we take our signals through our senses. Okay, through our senses. The senses are storing this information, and these are generating thoughts in our mind, which we don't know what they are, right? But we develop language to express those thoughts, to communicate, to speak. This part is not present in animals, non-humans, right? I mean, yes, they can, but they can make very, so this is very advanced in humans. So understand this, that this language is a mathematical structure, but thoughts have no mathematical structure. So what we are doing is that these are called hierarchical representations. So you can see it's in hierarchical. For this hierarchy, so this is X, and this is h1, this is h2, this is h3, and h4, and then y hat, let's say. I'll give you an example. So it's hierarchical. So what we will do is that we will make this. Did you understand? This is very important. You on example, I guess. I'm giving you. Did you understand this, guys? So what we will extend this? We'll extend this to this. So we have x, then we have w naught, b naught, h1. Then we have w1, b1, h2, dot dot. We have wk minus 1, bk minus 1, hk. And then finally wk, bk, y hat. So this is, so we have, this is just, so this is shallow and rest is deep. So the mathematics is simple. H1 is W naught x plus B1. This is a matrix multiplication. H2 is W1 x plus B1. H3 is W2 x plus B2 dot dot dot. HK is WK minus 1. Oh, I'm so sorry. I'm so sorry. This will be H1, H2, HK minus 1 plus BK minus 1. And finally, Y hat, the approximate is WK, HK plus BK. So you see this X is not used, this H1 is used. So these HIs are abstract representations. And this is why this is also why deep neural networks work so well. Because it's mimics how information flows through brain. Did you understand it, guys? So this is all about. So the Y hat can be expressed as this. First there is X, okay. Then W naught of X plus B naught. Then comes a activation function. And then again, on this comes W1 plus B1. So it's a WK plus dot. So this is a, it's called composition of functions. Okay, composition of functions. Did you understand it, guys? Yes or no? Vivan? Super. So this is just deep neural networks, and we have understood why these are really good. We have understood carefully that why this works so well. Now, next day, what we will do is we will explain a bit today. We will look into optimization of neural networks. So what is done there? Understand, if you remember that the main, so to repeat, for linear, Y hat was what? Y hat was this. For logistic, Y hat was softmax of this. Right? Simple. For shallow, y hat was a of. Now you can say that, I mean, you can say both. One for classification, one for regression. For regression, it was just a of w x plus b naught. For classification, there will be a softmax of that. For deep, it's again for regression. Let's do first regression. It's, we can say a, and so let's call it's this w comma b. Let's call this something. Let's call this hi is equal to w I minus 1 h. So let's call x naught is equal to h naught, and h I minus 1 plus b minus I minus 1 as some l I minus 1, some linear layer of h1. Let's define like this. So what we get, it's nothing but L naught of x, right? Then an activation function. I think I made a mistake here. It will be this. There's an activation function here. I hope yeah. There's an activation function here. So we can write this as a activation of linear layer, then activation 2, then again linear layer, then this, sorry, activation 2, and then linear layer dot L of k. And then find this is this. And then classification is nothing but this. But softmax. So do you see that these are special cases of this, guys? Linear, logistic, shallow are special cases of deep neural network, DNN. So now let's do a recapitulation of the how it's trained. So optimization is training, right? Optimization is training. Is finding the best theta. Finding the best theta. So how it's done? Let's see. For finding the best theta, what do? We use gradient descent. Right? We use gradient descent. So what do? For linear, so anyways, for any one of them, we use what? Theta n is equal to theta n minus 1 minus learning rate. I discussed it yesterday. The step size times the loss function at theta is equal to theta n minus 1. And we have said what are the two loss functions. For loss function for regression, we will use as of now as MSE, mean square error, and loss function for classification we will use as cross entropy. I have shown it yesterday what they are for K levels, C levels, let's say. So we will only use this in our course, nothing more, only two. There are more, only two for our course. Okay, there are many others, but there are many others too. So the question comes is that step number 1 is find the loss function between y and y hat. The y hat is already given here. Y hat are this. Step number 2 is find the gradient, the delta. This is a function of L theta, function of theta. You have to find derivative. You have already done it for linear and logistic. We will now do it for, because we need to use this for finding base theta. Finding best theta. So now we also need to find delta of this at theta is equal to theta n minus 1. And then solve it. Theta n, update the theta. These 4 steps are there. So we need to do all the steps, right? We need to do all the steps step by one by one. So next day, so let's try to revise the linear. Rather, I will give it as a homework for next week. Okay, and we'll discuss it. So next day, we will find gradients of linear, logistic, shallow, and deep neural networks. Okay, this is not an easy task, but it's simple. You will see it turns out to be simple. Okay, and once you find the gradients, that's why I stopped. We find loss. So we have discussed the loss. We'll find the gradients, and then we will see what other, and we will talk about something called backpropagation. This is yet to be discussed. So next day we will start with backpropagation. So this gradients to backpropagation. To backpropagation. Once we do this, then we will start coding. So we will code it from scratch. Then, so this will be the next week. And next to next week, it will be mostly about the other aspects, like how do we actually do it in real life? How do we do it in real time? There are many other methods out there. Like how do we make sure it's simple enough and stuff. So we will discuss the SGD and batches and epochs and all these things. Okay, so next week will be optimization deep neural networks. Okay, and the third day will be, it will be mostly about optimization deep neural networks with PyTorch, and this next week will be with Numpy, with everything Numpy. So it will be just simple. Okay, guys. So next, so yeah, so it will be optimizing with Numpy. So also revise your Python knowledge, and come next week we will be doing a lot of derivatives and a lot of Python. Okay, so essentially we will learning how to do this. And then next we will use PyTorch. We will learn everything how to train a deep neural network with some simple example data. And then a project will be given where you will be given a data set, and you can use PyTorch to find the results. Yes, tell me, Vivan.
So for the Python, do we need to know how like the numpy works, or will you?
Yeah, you need to know how NumPy works.
Okay.
So read about it. I will give a tutorial
Okay. Okay.
example. Okay, it's very simple, but need to know. I mean, so the thing is that I will automatically tell you how NumPy works while doing it, which are necessary. It's nothing but a new language. It will be 15 minutes to learn and like understand. So it's
Okay.
good to do some exercises before so that you are aware of it. Okay, but anyway, I will tell you what it means. Like so essentially it's matrix multiplication. Okay, and also plus Python basics.
Okay.
Like
Yeah.
object class and ODI, like this, objects, etc. Okay, got it?
Yeah.
So it will be gradients, derivatives in matrices. So, and the implementation in PyTorch. Okay. Any questions?
No, sir.
Okay. All the best, guys. I will see you next week. Bye bye.
Yes,
Oh,
sir. Thank you.
bye. Thank you.